Now let's see how this matrix factorization techniques are helped to a clustering algorithms. So already we have learned in the unsupervised modeling series that there have mainly three types of the clustering technique, means k-means, then hierarchical clustering, and the third one is we have that learned the third one that we have learned. Third one is Deep-scan algorithm. Okay, the first one is k-means, second is hierarchical clustering, and third one is Deep-scan or density-based clustering. These three kind of clustering technique already we have learned. So now let's try to find the relations between matrix factorizations and the clustering. So in these discussions, we have taken the k-means algorithm. If you just remember, in k-means, in clustering technique, means in any unsupervised learning model, the data sets that we have like that, xi. Okay, this kind of data sets we have. Now our job is to find the nearest point, of the data. Nearest means a closest point, closest kind of points to these data sets. Okay, we have to find the clusters from our data set. That's the job that we have to do. So first thing, if you remember the k-means clustering, if you remember the k-means, then the objective functions of the k-means, primary objective functions of the k-means is look like this. Or we have to find the arc mean. Arc mean, we have to find the H cluster. Suppose let's take Ci our cluster, and this cluster will be find on based on these points, based on the simple distances of the x minus the centroid at Ci. This is the centroid of the cluster Si, that we have already learned. This value, the number, suppose when the x is belongs to the cluster Si, and this is for applicable for all cluster. I is equals to 1 to k. K is the number of cluster. That's we have seen. That already we have seen in one of our previous discussions. Okay, and these things must be square distance. These things must be square distance. Okay. Suppose let we recall these equations as 1. We call these equations as number 1 equation. First note these things, what is k, what is c, what is this. So k is here. Here k, the variable k is responsible of number of clusters. Number of clusters. And Si, that Si is the set of all the points that belongs to the cluster I. Okay, so it is the set of all points that belongs to the cluster I. So I value will be here, I will be 1, 2 up to k. Means there have we consider then there have k number of cluster. So here I will be 1 to k. Okay, and the x that we have considered here, that x belongs to x is the data point. X is called the data point. Okay. X is our data point. Okay. Now the thing here, the property there Si that we have to always remember. The property for Si is H different Si must be the intersection of H different Si must be an empty set. Here I not equals to j, and for all I and j belongs to 1 to k. Okay, that's the first property, means the H cluster or there have no any common point in H cluster. Okay, that's the first property that we have to remember. And X is the data points. X is the number of data points. Okay, so these things are actually referred to, means what? These things x minus ci refers to the distance of the point to the centroid, and ci, the thing is better if we write it. Ci is the centroid of the cluster Si. We have already seen this thing. Centroid of the cluster Si. Okay, that things already we have seen. So here also the number of centroids will be also 1 to k. Okay. So now this thing, now this is the x minus ci whole square, means I am talking about this whole term. It will be k. I am talking about this whole term. This whole included with square. Okay, this term is refers to the distance of the point, distance of our data point from our the centroid, that the point that the point lies on the cluster. So the ci is the centroid of the cluster Si. So x is those points are lie on this centroid, on this cluster Si. Okay, we have already seen, and now our target is we have to find those clusters. That's our target. Okay, that means this is our objective functions. Based on these objective functions, we have to find this ci. So these things are refers to the, these are refers to the distance of the point x from the centroid. Ci, that belongs to the cluster S. Okay, that's the job, that things refer the distance sample. Sample in general we have taken the Euclidean distance. Okay, that's already we have seen in the k nearest neighbor chapter. And the one thing that we have to remember here, the distance that we have calculated here, only if those points, those are belongs to only this cluster Si. Okay, so these things always we have to remember. The thing that always we have to remember, that the distance that we have collected here, if and only, this is the short symbol of if and only if and only if the points, if and only if the data points belongs to the cluster Si. Belongs to the cluster Si. Only then we calculated this point. Otherwise, this value will be 0. Else this norm of x minus ci their whole square is equals to 0. Okay, if and only if these points lie on this cluster, only then we have considered these functions. Otherwise, we will not consider. It's equals to 0. Okay, now based on these situations, we have to calculate it a function. We have to find a function. Okay, so how we will find this function? Let's see how we will find a function. Now let's see, before finding the functions, we have to construct one thing. We have to construct a matrix that's related to the centroid and the number of data points. And based on this matrix, we have to calculate a function. Okay, now let's see. Let's construct the matrix part. So we have to construct a matrix Z. We are interested to construct a matrix Z. So the Z, the matrix will be look like this. Okay. So the in row vector, the row of this matrix will be responsible for each cluster. It means H centroid. So here how much centroid? For H cluster, for K cluster we have K centroid. So the row of this matrix J is responsible for H centroid. C1, C2 like that. Somehow let's take it's the Ci. Let's take somehow it's the Ck. A cluster, and the each column vector is responsible for each data point. Okay, so we have how much data points in our suppose let in the data set D we have n data points. Number of data points in our set is equals to D. So the column is responsible for the number of data points. So n data points we have x1, x2, suppose let somehow here xj, let somehow here xn. Okay, somehow here xn. Let these are the responsible. So the dimension of the matrix Z, now it will be a row corresponding n column. That's the dimension of this matrix J. So if we consider this is a common row, this is common row, and this is the for our responsible for common column. This is responsible our common column. Then this value here it will be Zij. Suppose let this is the Zij. Let now we have to define this Zij such a way that's fulfill this property. Okay, that's fulfill this property. Okay, how we'll see that if you just remember this property. If you just remember this property, if the data points lie on the cluster I, then we have considered this distance, else otherwise we have neglect, means this equals to 0. So based on this property we have to define the formula of this Zij. Now let's see how these things we have defined. So the definitions here, the definitions of the Zij will be look like this. The value of the Zij will be 1 if the data points xi, if the data points here xj, we have taken the xj, if the data point xj is belongs to the cluster si. This is responsible for what? This one is responsible for the cluster si. This centroid is responsible for the cluster h1. This centroid is responsible for the cluster h2. This centroid is responsible for the cluster sk. Okay, just this is the Z, capital Z. Okay, we have to define this Zij such a way that it will be 1 if the data points xj belongs to the cluster si. Only then if this data points only belongs to si, then we have considered this distance, then we will calculate this distance. Otherwise we have not calculated. Because of these reasons we will define this function in such a way like that. Si, I'm using the same color here. Si, else otherwise its value will be 0. Otherwise its value will be 0. This is the function that we have to. I think you will understand why this function why we have defined. I think I got the idea from these regions. We will define this. Now let's try to understand these functions in more deeply. Why actually these functions are talking about. This is the very important part. So suppose let if this value z23, we have considered z23, somewhere here we got 23 is equals to 1, we got it. It implies that means what? It implies that the data point x3, this j, data point j, the data point x3 belongs to the cluster 2. This data 3 belongs to the cluster 2. Okay, that means that. And if suppose let z32 is equals to 0, that means what? That means the data point x2 does not belongs to s3. Okay, that means I think you got the answer why how these functions are actually look like. So the basically the matrix Z that we have defined here, that tells us which data points belongs to which cluster and what is its centroid and what is not. Okay, that's the matrix is actually talking about. Okay, so the matrix that we have defined, these matrix are talking about the tells us which data point, which data points belongs to which cluster. Which cluster and what is its centroid and what is not. Which cluster, what is its centroid and what is not. What is not. This kind of informations we can get from this matrix. Now the questions that come into mind, at the end of the day we have to find this cluster. Now how we will use this matrix as a matrix factorizations problem, how we'll convert this matrix as a matrix factorization problem. Now let's see it. So now let's try to implement this matrix Z in this function. Let's try to something implement it. Means instead of this concept that we have got, we will simply use this Zij concept. Zij, just we imply it. So if we imply these things, that means if we simply imply these things, that means the objective functions what we have. Let's rewrite first. So the objective functions that we have, the arc mean of, we have to find the Ci, and at the end of the day we have to find the those xi distance from the Cjth cluster. Okay, that's the square, and this xi is belongs to the cluster Cj. Sj, sorry, Sj is the cluster and Cj is the its centroid of this centroid, and this j will be, this j value will be 1 to k. This j value will be, so I here is the j. Okay, j value is be 1 to. Okay, I think you got the idea how these things are actually happening. Just we already discussed these things in this. As instead of using x here, I am using here xi, and instead of using is I have used here sj. Okay, everything is okay. Now if we have to change little bit here. Okay, we have to change little bit. How we will change this thing? Means we have seen here, if these data points is lie on that cluster, then Zij is equals to 0. That means what? That if we just simple use this thing, if xi belongs to sj, if this thing happen, that means what? That means j is equals to 1, else otherwise Zij is equals to 0. Okay, means if we just simply include this term here, if we include this term here, that does not matter. Actually at the end of the day does not matter, because if we include 1 here, if we instead of using 1 here, so it does not matter. So these calculations are doing the same job. Okay, so now let's redraw these equations like in that format. Now rewrite these equations in this format. Same equation, just I am rewrite it again. Arc mean of Cj, where j is from 1 to k, and here xi, So here I instead of zij, norm of xi minus dj square whole square, and this zij, that's I now, it will be responsible for our number of data points. Okay, here this j means this j cluster, and this I responsible for number of data points. This I, okay, Sama. This j is responsible for what? Number of, this j is responsible for number of data points. This j is responsible for number of data points. Just draw this thing. These things is data points, and this I, just using this I, is the cluster number of cluster. Number of cluster. Okay, so because of this thing we have to use here, just change the color here. For example, using the data points, we have here I. So I, and I is the second positions here, second position, and first positions is I for cluster. First position is responsible for cluster, number of cluster, and second is number of data points. So here j is responsible for number of clusters, so it will be j and it will be I. Okay, I think you got the idea why these things happen. Just compare these things on this through these equations. Okay, first position is responsible for number of clusters, second is number of data points. Here, so for using j, we are using here j for denoting the number of clusters and I for number of data points. Okay, because of this is the clusters, this is the data point. Clusters, this is the data points. Okay, so just see this thing. Okay, IB, you will got the point how these equations can come, each come. So if we compare these two equations side by side, if we compare these two equations, then we got when jet ij, when this j, this I think it's equations number 1, I denoted it. This is the same equations as 1. Just write it 1. Just write it as 2. Okay, when jet ij, using the definite color, when jet I is equals to 1, into, if this is 1 into, then that implies what? That implies that xj means, so what here, xj is responsible for here, just 1 minute, j is responsible for here number of cluster, j is responsible for number of cluster. Okay, number of cluster, and I is responsible for number of data points. So that means the data point xi is belongs to the cluster is j. Okay, in 1. Okay, and when zi is equals to 0 in 2, that implies that xi does not belongs to the cluster is j in 1. Okay, that's the same thing, just I am rewrite this thing. Both the equations are the same, just we have include this concept of the j. Now our main job is we have to convert this formula, means in this formula we have considered all the data points, but here we have not used this thing. That's the main advantage here. So we have to consider all the data points in our calculations. On this all the data points, we have to compute the centroid. Now how we will convert this objective function? This is the now objective function. This is the objective function. Okay, this is the objective function here. Now the question is, what will be the constant, sir? What will be the constant? Now let's try to understand what will be the constant here. So first see this thing. First see the Z matrix. So the Z matrix that we got, it's either 0 or 1. That's the first thing. So first constant that we got here such that the Zji is equals to 1 or 0 for all j. For all j that we have taken, means j is responsible for number of clusters, means 1 to k, j will be 1 to k, and I will be, for all I will be 1 to n. That's the first constant. Second constant is, just see it, each point there must be lie on a single cluster. It is not possible to lie it is in a two different cluster, because the property of the SI is like that. SI intersection Sj is equals to 5, means for different two clusters it's not possible, they have no possible for a common point. Okay, because of these reasons, this xi, this xj point only lie on a single cluster. Because of these reasons, if this is 1, then the rest of the will be 0. So the summed value of xj, so the if we consider here the summed value of xj, this summed value of xj, okay, where this j value, summed value over all j, means I am talking about all the sum, all this sum is equals to what? Is equals to, it will be 1. Okay, I think you got the idea here. It's another constant. So the sum of j I is equals to 1. Here I is for what? Number of cluster over, then k is equals to 1 to k. Okay, for all clusters, means these sums that we have to take. For j is equals to 1 to k. Here j is equals to 1 to k. This will be 1. This is the second constant. Okay, these two constants we have to use to find this objective function. In one of previous lecture, we have seen how to find these objective functions like a matrix factorization problem. By simple, you can use the stochastic gradient descent. It is a simple technique to solve this objective function. Now let's try to understand these objective functions to a matrix factorizations point of view. Let's try to understand it. So first let the data point that we have taken here, the data points, that means x is the data points that we have taken. Suppose it's the xi, it belongs to the d-dimensional data point. Let's take it. Okay, let's take these, the data points is the d-dimensional. It will be better for easy to understand. It will be better for understand. So the data set here, the data set is look like this, xi, and this I is from 1 to n, and xi is belongs to the d-dimensional point. That is the part. So first, based on these things, we have to build the data matrix, data set matrix. So the data set matrix will be look like this. This will be the simple structure of our data matrix. So in each column, we have taken the number of data points. So how much data points we have? N data points. So for this, we have used here 1, 2, somehow here xj up to xn. This is, and here we will define these things for the dimension. Okay, since h points is lie on the d-dimensional point, so this h row will be responsible for the dimension. Somewhere I, somewhere here it will be d. So this h, now Now this H column is our data set. Now H column is our data set. This thing. Okay? This is the this Hx2 is the data point. Data point. Okay, H column is x2 is the data point. And what will be the size of this matrix? Here number of data points n, and how much row we have? D row and n column. This is the size of the matrix. So since the data sets is belongs to d-dimensional, since if we have the d features, then similarly in our centroid that things will be also d-dimensional, because centroid is also lie on our data set. That's the first thing. So the H centroid, H CJs, have used the CJ, I think. Yes, right, CJ. So the CJ will be 1, 2, 3 up to K. K that must be belongs to HCJ must be belongs to the d-dimensional set, d-dimensional space. Okay, and also J is from 1, 2 up to D. Similarly, we have to define the C set by using these things. C set, we have to define the cluster matrix D. This is the centroid matrix. This is called the data matrix. This matrix is called the data matrix, and the C is called the centroid matrix that we are going to find. This is called the centroid matrix. Now the structure of the centroid matrix will be look like this. Okay, so here in column we have used the data points, but here in row we have used the column points. So here we have in row means CJ, D means CJ, J is equals to number of clusters, means that it will be K. So here it will be first row is responsible for first centroid, second row is responsible for second centroid, third row is responsible for third centroid. Similarly, it's the ith row, it means suppose let is the I am taken here ith row. It's always better to take the ith row in jth column, and this is the K. So since they have the K centroid, and H centroid is the d-dimensional point. So the column that we have taken here is a d-dimensional. It will be up to D. So here H, here H row is for H centroid. Here H row is the centroid of the cluster is I. Okay, and d-dimensional it is. I think your idea got the idea. And what will be the dimension of it? So dimensional here K row and D column. K row, D column. That will be the. So now what is the relations between D and C? Just see it first. So first, what is the dimension of the Z? Z dimension is the K into N. Somehow we have to find this Z by using this matrix X and C. Just see this thing. It is possible if we doing the multiplications C into X, then D and D will cross out, and it will be K into cross N. So this is the same dimension of the Z. Okay, just this kind of idea we have to apply here to find this matrix Z. Okay, now let's see how we will find this. How we will find this thing. So to find this idea, we have to use one concept, the Z. So if you just see the structure of Z, Z is a very sparse matrix. Yes, Z is a very sparse matrix. Okay, Z is a very sparse matrix because only one element lies on a single cluster. Because of these reasons, this Z is a very sparse matrix. That thing always you have to remember. It is a sparse matrix. And the concept that we have used to develop this factorization problem. So the Z is a sparse matrix, means Z has a sparse column, mainly the sparse column. Okay, the Z has mainly the sparse column. Okay, because only one in a column, only one will be here. Okay, because of this sum will be 1. So mainly this is sparse matrix, mainly each column is a sparse column. That's the thing. So J it has a sparse column. That is what? That is only one value in each of its column will be 1. Okay, that is only one value of each of I think in will better language, value in each of its column will be 1, because only on that it is parts, and this is the simple reason, because only one point lie on a single cluster. Because of this reasons, only one value in each of its column will be 1. Okay, while rest of the other 0, while the rest values are 0. Okay, this is the, as there can be only, since why these things happen, because there can be only one centroid in each data point. Okay, because there can only one centroid for each data point. Because of these reasons, these things happen. This is a sparse column. Now let's see. Since it is a sparse column, means just that the idea that we have to use. Means here only a single, for a single column there are only one. So this one actually represents the which data matrix going to which classes. That's the actually this data is here talking about this, which data point is going to which classes. Okay, that's the idea that we have to. So suppose now let's try to use here. So here in X the column is represented the data points, and the in C the row is represented at the centroid. Okay, if we somehow multiply these two matrix, means if we multiply the Ci, means I row of the centroid matrix and the j column of the data matrix, then what we will get? Let's see it. Let's see it first. So now that we got here Ci that we got, Ci is the ith row, Ci is the ith row, I think, yes. Ci is the ith row of C. Okay, and its dimension is equals to its dimension of this Ci is dimension is equals to what? How much? Single row D column 1 rows D. Now we have to use, somehow we have to find this centroid is responsible for which data points, and that's the concept that we got from this Z matrix. Okay, now we have to somehow we have to use this Z value, this value X, this value. then we can got it. Now let's see how we'll do. Ci is the row of C. Okay, and its dimension is 1 cross 1. That's the first thing we have to remember. The second thing that we have to remember here, the zj means is the j column of, suppose let's take this is the xj instead of this j. I am using here zj. I am using here the zj. Okay, because x also already we have used here in X matrix. I think it will be better for if we denote it with the j. Okay, for j matrix. And the j bit is the jth column of the matrix Z. Then, and let's see the dimension part. JZ, what is the dimension? Here we have the k row and single column. So k cross 1, its dimension is k cross 1. Its dimension is, so its dimension is what? K row, it is as 1. Okay, now let's multiply these two things, Ci and Zj. It is possible using the multiplications. Just see it. Is it possible? I think you will just try to understand, is it possible or not. You can show, sir, it is not possible since the Ci, the dimension of the Ci is 1 cross d, but here the dimension of the Zj is equals to k cross 1. But see this thing internally. Okay, so since it is not possible here to the multiplications, just see here d, here k, it is not totally possible. So our assumptions that we have take here is wrong. So we have to, instead of, if we want to multiply it, instead of considering this d, means it's, we have to convert this d somehow k, then it is possible. So instead of using this row, if we consider the column matrix, then is it possible? I think then it is possible. Okay, so now let's see if we consider the column vector of this matrix. Okay, column. So instead of using this row, we have column. I use the column ith. Okay, so the ith column, suppose let's take this column is, let the ith column of C. I have somehow it's denoted the C dashed, let ith column is C dashed. It is the row is C1, its column is, suppose let's say C1 dashed, C2 dashed, C3 dashed, CJ dashed, so CD dashed. Okay, somehow let D dashed, CD dashed, column I have taken. So if we just column taken the column, so hence you have taken the jth, I am using the ith column. Ith column. So what will be the dimension of the ith column? So it has the how much row in this column? K row and single column. So this dimensional will be, now this dimensional will be k into k row into single column. So if we want to now multiply, we have to make this transformation, transpose, then we will got it. So now if we multiply these things, now if we multiply Ci dashed transpose into Zj, if we multiply this thing, that means what? Let's see, Zj Ci transpose. Now this I value will be lie on what? This I will be responsible for 1 to d. This I is, this I will be 1 to d up to d, and this j, now let's see the j is also 1 to n. Okay, so this this I will be what? Just write this thing very clearly. Now this I value, this we have taken this column vector to a transpose, so it will be converted to a row. So Ci, just Ci first, Ci means Ci1 to up to k. K means they have how much value? K dimensional. This will be Ci1 C dashed, sorry, C dashed I2, C dashed I3, like how much? This value is for how much? This value is for k value, k, such kind of C dashed I k. Okay, just I am taking transpose. So column vector will be now transposed to a row vector into this is the zj column. Let's see the zj column. Since it will be zj1 to k, this value will be zj1, zj2, I think zj. This is a column, means first we have to use the row 1j. Okay, that's my bad. z1j, z2j, up to which, let's see the z first, z up to kj, z up to kj will be kj. Now it is possible for multiplications, here also k dimensional, here also k dimensional. If we're doing these multiplications, then what value we got? So we got c1 dash c dashed I1 into z 1j plus c dashed I2 into z 2j plus c dashed I3 into z 3j plus up to c dashed ik into z kj. We got this value. Okay, if you just simple doing this dot product. So now let's try to understand what is the significance of this value. What is the significance of it? Let's try to denote these things as a equation 3. Now let's try to denote this as a equation 3. So just see this, this part zij is either 0 or 1. Actually it is our the constant part. It is actually our constant part. Either it is with 0 or 1. So since it is the 0 or 1, so only in a this, and also this is a column vector, means since this is a column vector, only one, it is only here only one term will be 1. So the trace term will be 1. So because of these reasons, they are erased. Because of this reason, here on this kth sum, on this kth value, we got only one value. Okay, so the significance of these equations is look like this. The meaning of these equations, only one of the terms of these equations is non-zero. Okay, only one of the terms of equation 3 is non-zero, as there can be only be one centroid. Since why these things happen? Since for a data point it is possible for only a single centroid. Okay, as there can be only one centroid per data point. Because of these reasons, they have only one term. Okay, because only of this reason. Okay, so this says this now this matrix Ci transpose Z Ci, that I am using a single column, single row, single column. Just I am using the single column from C and single column from the Z. Just I am in a single column. If we consider all the column, so now this matrix can be now this matrix. So the C transpose that we have considered here, C transpose, the C matrix is what? This is C matrix. This is C transpose because we have using the transpose. C dash is the transpose of the C dash is the column. Okay, C dash is the column. So the C transpose, if we transpose it, C transpose Z, effectively it carries to the only those data points which belongs to a cluster. So just simple see the single cluster, the single multiplication, the single column. If you consider a single column, the single column refers to those points which belongs to only one cluster. If we consider the whole matrix, that's effectively carries only those points, those data points which belong to a cluster. Okay, because of this refers to these carrots these carrots only those data points which are belongs to a cluster. I think you got the idea. This is the simple idea that we have taken here. C dash, okay, that we have taken here. This is the C that we have taken as a centroid data points. So I think it's better if I using this C edge like this. C dash transpose means C dash transpose have used here. So C dash is the column, so it will be simple C value, it will be here. Okay. So I think it's better if we just you are using this concept C, means I am using this C's d-dimensional concept here, like this way. Just write the C transpose in that way. So instead of using C transpose, so write here C is equals to this matrix, column matrix, means the C1 is C2 is to K centroid. This is actually K centroid. So instead of using this centroids to a row matrix, just using as a column matrix, I think it will be now better. Just simple use the C transpose. Here it's dimensional 1 up to D. So now its dimension will be D cross K. Okay. So now instead of using this, okay, centroid of the cluster, these are this column. If we consider this matrix, means if we simple transpose this matrix, if we simple transpose this matrix in like that manner, so I think it will be better for us. So then we can simple use this C term here. Okay, I think you got the idea how these things are actually representable by simple the C and Z form. Now the conclude, if you conclude this part, if you conclude this thing as like this way, means we have to Actually, we have to find the data points. We have to find that we have the data points, and the data points is like that. Its data points is lie on a H cluster. So that's give us this matrix, and the data matrix that we have X. If we somehow express the X matrix is look like this format, C into Z. If we express somehow this format, then we can conclude that our objective is done. Means this C into Z means gives us what? It gives the only those data points which belongs to a single cluster, and X is our the data points. If we somehow express this X to this matrix, then our job is done. So to find these jobs, the objective function that we have to define here, the objective functions is, it will be the minimum of argmin, means that argmin of over whole Z. That's the thing that we have to find, Z and C, and this is the objective function. It start Z, a whole square must be. Okay, that's the objective functions. Okay, and the constant is such that the constant is this, that is zeta is 0 or 1, and is Zij is equals to 1. The constant is either 0 or 1, and the summed over what? Zij means that thing, Zj that we have taken. Just instead of just write it in a sum of the column of Z is equals to 1. Sum of the column of the is equals to 1. That's the two constant that we have to. So this is the simple mathematical optimal problem. This is the simple mathematical optimal problem, and this is our objective function, and these are the constant. These are the constant. This is the simple job that we have to do. Yeah. Okay, I think you have understand this concept, how these matrix factorizations have actually used in clustering technique. I think you got the idea from this whole discussions, from the huge discussions. Okay, so before going to ending this video, one thing that we have to visualize, it's also an important part. So the one thing that we have to visualize, we can compare this optimal mathematical optimal problem to a non-negative matrix factorizations concept. So what we have seen in non-negative matrix factorizations concept, so we have to matrix factorizations, we have to make the matrix factorizations, we have to find some two matrix that will factorize each other, and the in non-negative matrix factorizations we have seen the constant that we have, it's a non-negative number. It's a non-negative number. Sorry, Ij it will be. It's a non-negative number, but here that means clustering, means this clustering means one kind of. But here in clustering that we have got, we have to find Z and C. That okay. But the constant here is the zeta is equals to either 0 or 1, and the another constant is this kind of thing. Okay, and another constant is column sum. Column sum of Z is 1. That's the two constant. Means you can consider here this kind of problem, this object, this mathematical optimum problem is like of a non-negative matrix factorizations problem. So this is the simple mathematical hacks that we have to use by converting this clustering problem, this beautiful clustering problem to a matrix factorizations problem. So I think from these discussions, from the details discussions, I think you got the idea how the mathematics behind its work actually. So first, the thing that we have to build, we have to individually build the three type of matrix. X means data matrix, C means our centroid matrix, and the Z that's defined the which point will be lie on which cluster. Okay, and the constant that we have to take the property is each point must be lie on a single cluster. Based on that we find the relationship on this three matrix is look like these relations C into Z, this matrix multiplications gives us the result only those data point which belongs to a single cluster. Because the multiplications result that we have seen, only one term will be non-zero and rest of the term 0. Because of these reasons, this multiplications result C into Z gives us the result only those data points which are belongs to a cluster. Okay, and this matrix multiplication gives this result, and these results actually equivalent to our data matrix, and just only we have used this concept to build the matrix factorization objective function. Okay, and we have to use this cluster to build our optimal problem. I think from these discussions you got the idea how the mathematics behind it are actually work. Okay, I request you, if you have any problem, please comment below. I will always here to help you. Okay, I will always here. Okay, I think if till now if you have not understand, please recap this video, and after that if you have any problem, please mail me or comment below. I will try to give this explanation as simple as possible. Okay.